Today, we're going to be talking about one of our solar charge controllers, which is the Conext MPPT80 600. I am going to cover best practices for programming, wiring, installation for this unit. Quick overview of our product portfolio. Like I said, today I will be talking about one of our solar charge controllers, which is the MPPT80, but we also have our MPPT60 150, which is the other charge controller. Our main inverter today is the Conext XW Pro. Although not shown here on the screen, we also have our SW models, which are our smaller inverter. Some of the accessories, power distribution panels in the mini power distribution panel, and I will cover our rapid shutdown solution later in this presentation because it is relevant to the MPPT80. So let me jump directly into what we are here to talk about. The uniqueness about the MPPT80 600 is because it can accept up to 600 volts, which makes it a little bit more similar to what a residential grid tie inverter is. So typically what you would do with the MPPT80 is strings of 10, maybe strings of 12, depending on the module. Of course, today modules are getting bigger and bigger. And usually the typical installation has 1 or 2 strings. The output is 80 amps. Out to the batteries, it will be 80 amps. And remember, this is a DC to DC device, right? So it takes the higher voltage from the array and steps it down to the battery voltage. And the battery voltage for this product can be 24 or 48. It will auto detect on commissioning if it's connected to a 48 volt battery or if it's connected to a 24 volt battery. So you can buy the same product for different systems. It does have a fan, and we'll talk a little bit about the cooling of the unit when we look at the best installation practices, but it will operate with no D-rate all the way to 45 degrees C. So the output 80 amps all the way to 45 degrees C, and can be used in different grounding systems. Most common today is what some call ungrounded systems, although I really don't like that term because the system is grounded, but what you're grounding is all the metallic areas of the array, the frame of the modules, and so you are actually grounding the chassis of the system, right? But in some rare cases, we are required, sometimes for the module manufacturers themselves, to do a positive grounding or a negative grounding, and this product is compatible with all 3 grounding styles. It has a built-in ground fault, and because it communicates with all of the other Conext products, of course, it is network is a Xanbus device. Xanbus is our communication protocol. So this solar charge controller can actually talk to the Schneider inverters. And I will share with you later as I'm talking about programming some of the benefits, although it can work alone. So you may have a system that is DC only. It doesn't need an inverter to operate. So if you had maybe a system that is only DC, like in some telecom operations, this unit can operate without an inverter. But if the inverter is in the network, and if the inverter is a Schneider electric inverter, then it can communicate, and we can actually monitor the performance through the monitoring and control platform, which is our Insight tool. The input, which is on the PV side, is 28 amps, which is fine because you will typically have 1 or 2 strings, so you'll unlikely exceed that. It has a high efficiency of power conversion, which is at 96% for a nominal 48 volt system. I mentioned before that it can work on a 24 volt or a 48 volt. The array changes a little bit, right? Because when the voltage decreases, like in the case, so going from 48 to 24, the array size is going to change. So for a 48 volt nominal system, that means the batteries are 48 volt nominal, the array is about 5,000 watts, so 4,800. However, oversizing is perfectly acceptable. Remember when we first started talking about this product, I compared it with a grid tie inverter in the sense of the 600 volt stringing of modules. But there's another thing that we do with grid tie inverters, which is very common in the industry, is oversizing the array. And there's many reasons why we oversize the array. Maybe the orientation of the array is not ideal. We are also having to accommodate for losses of the modules throughout the life expectancy. So it's very typical for an array to be oversized by 20, 25%. I've seen arrays oversized more than that in northern hemispheres with solar irradiation is not optimum. So I will say that again, comparing this product with what I will call a grid tie inverter is perfectly all right to oversize the array. So the 4,800 watts can't be oversized. So if you have a 5,000, 5,200 watt array, it's perfectly okay. Now, and one thing is that say you have oversized the array, but you have optimum irradiation. The array is in the perfect angle. And the only reason why the array was oversized is because we were trying to accommodate the losses that the modules will suffer across the life expectancy. What's going to happen in the very beginning is that you're not going to output more than 80 amps. So you will see some clipping on the peak sun hours, around noon, right? So again, oversizing is okay to accommodate the life expectancy of the system. However, the output is 80 amps. So that will not change. The solar charge controller is going to charge the batteries in this very typical 3-stage charge. So every day, what we should see in a properly sized system is that the solar charge controller wakes up in the morning, depending on the solar irradiation and the angle and what time it'll wake up, and it will start charging the batteries in this first stage, which we call bulk stage. The voltage in the current is increasing until I reach a preset set point, which is programmable. And then the unit will transition to the next stage, which is called absorption stage. In the absorption stage, now we're at constant voltage. So the solar charge controller will maintain a constant voltage. And the uniqueness of this stage is that now the current doesn't track. Now the current, I'm using my mouse here as a pointer, but you would see the slope going down of the current. The voltage will stay the same because this stage, the absorption stage, that's the last part of the charging for a lead acid battery. So traditionally, we say that a lead acid battery, once I've reached the bulk voltage, we are about 80, 90% state of charge. We need the next stage, which is the absorption stage, to complete the charge. Once we reach the end of the absorption stage, then a lead acid battery should be fully charged. The next stage, sometimes also called trickle charging or float, just to simply maintain those batteries. So this is a very typical profile of what will happen in a day for a lead acid battery. The popularity of lithium batteries, and I will talk a little bit about lithium later on, you will notice if you have been working with lithium batteries in the past that they don't require these stages. They just simply give you 1 volt. The majority of them just simply give you a voltage. And that's perfectly fine. So with the programming, and I will show you later, we can just simply disregard all of these stages and provide same voltages for all of them. And that will meet the requirements of a lithium battery. So we don't need to do the stages, and that's all accessible via the programming settings. So the MPPT80 has our patented fast sweep algorithm. This is a maximum power point tracker. We all do maximum power point tracking differently. So you hear about grid-tie inverters and other charge controllers that are maximum power point tracking. We all do it a little bit different. The end result is similar. However, with our patented fast sweep, what we are doing is identifying the perfect spot in the array rapidly, which actually translate in greater production. Okay, so what is this maximum power point tracker? So what's happening is if we look at this, we see that the best spot is this point where I have the most voltage and the most current. So equal the most power. Okay, so why is it important that we sweep the array, and why is it beneficial to have this fast sweep? So let me switch here to my next graph. And this is actually what happens with an array. The maximum power point is constantly moving. It isn't a fixed point. So if a grid-tie or another charge controller wasn't dynamically trying to look for the maximum point, then it would actually lose production. It would not harvest the maximum. So what are the things that make this perfect spot, the maximum power point, move? Well, irradiation, the angle of the sun, and temperature. Right? So it is very critical that PV inverter or the solar charge controller is the maximum power point tracker. But additionally, having the patented Schneider Electric patented fast sweep makes the MPPT80 even faster in tracking the best spot, which translate maybe not day to day, maybe it's not something you will be able to quantify day to day, but you can definitely quantify at the end of the year a significant increase in production. So here is a very typical architecture of a DC couple system where we are incorporating the MPPT80. So the uniqueness of a DC couple system is that the array is managed by a solar charge controller. In this case, I'm showing the MPPT80. I already mentioned that this device is a DC to DC device. So the array, higher voltage up to 600 volts, and the MPPT80 will step the voltage down to the nominal battery voltage. From here, then the Schneider Electric XW Pro or SW will take that power, directed based on the selection from the owner. So for example, I can have a system that is completely off-grid and the customer is completely dependent on the production of the array. In that case, the inverter will take all of the array production and support the customer loads. Or maybe I can have a system that is grid-tie. In that case, the customer may have two options. They could have self-consumption, or they could have what we call net metering, where I'm allowed to export out to the grid. So the uniqueness of having the Schneider system in all of the devices connected to the Xanbus network is that now I can actually communicate between the devices and decide at what point I have excess power. Let me give you an example to clarify what I'm trying to say here. In most cases with storage, in most cases where a customer is requiring storage, what we are asked is that the storage is held for an emergency. There's a power outage, so the customer wants to make sure their batteries are fully charged in case of a power outage. So the priority is the solar array will charge the batteries first. However, in a grid-tied system where you haven't had a power outage, the batteries are going to be full from the day before because if you don't use the batteries, they don't just simply discharge overnight. The idea of having the solar charge controller and the inverter together in the same network is now that the inverter can get information from the charge controller and decide to start exporting power out to the meter earlier, what we call enhanced grid support. For the MPPT80, what you see in front of the unit, you see these LED lights. So it doesn't have a UI or user interface. And you have heard me talk about programming, and there's some programming requirement, and I'll show you what that is. The system, because it is in the Xanbus network, the MPPT80 can be programmed with the system control panel, which will be part of the network. Here you program inverters, charge controllers, or you may have a gateway in the system. And the gateway will actually allow you to program all of the devices, either locally while you are at the site, but also allow you to access them via the cloud or inside too. And you can actually program the settings using the cloud remotely, locally using the gateway. And you see that the gateway doesn't have a screen. So what you actually do is you connect to the gateway with your cell phone. So it has a hotspot. So you basically connect to it. You see all the settings through your cell phone or the older style using the system control panel. So either options are available for the actual programming, which will be a section of my webinar a little bit later. But now let's look at part of the installation. The unit is NEMA 1, which means it has to be installed indoors, protected. It also has a requirement of a vertical installation. So what you're seeing on my screen is actually the only way that this unit can be installed. Okay, so you're going to find knockouts on either side. They're exactly the same. So these knockouts vary in size. For the conductors, you have the same exact knockouts on the other side, and you also have them on the back of the unit. Okay, so you'll find knockouts on the sides and on the back. And the very bottom, you will find a screen and no knockouts, because this is where the unit will actually have air intake. Don't block the bottom because that's how the unit ventilates. You'll have 2 fans on the top, and so it is extracting or pushing the air up. So that, for that reason, is that you need to give the unit a minimum clearance from the top and the bottom. And here I'm showing you a dual, and you see them side by side. That's perfectly okay, because there's no air movement on the sides. So as long as you leave enough space from the bottom and out to the top for the fans to move the air. This is what a real system looks like. It was designed as exactly the same size as the PDP, the XW Pro PDP combination. It lines up perfectly to one of the sides of the PDP. And the knockouts here match exactly to the side of the MPPT80. So you can run your PV as well as your battery cables. Here's another photo of a real system, and this system has 5 MPPTs and 3 of the Conext XW inverters. Let's jump into the wiring compartment now. The first thing I want to point out, and only because I've run into a couple of problems with this barrier. It's actually a plastic barrier and it's easily removed. And it was actually designed so that you can actually run the wires, do all the wire running, but it needs to be reinstalled. So if you're going to remove it, just to make easy installation, don't forget to put it back, because this barrier is actually separating the conductors with higher voltage. So this side is the array, which is could be up to 600 volts, and then this other side is to the batteries, and that's 48 volts. So you don't want to mix those two. So the barrier is actually part of the UL listing of the product, and you don't want to mix the two wires. One more thing here, and I think the next view will show it a little bit better, but this piece here is an aluminum tray intended for the communication cables. So you want to make sure that you're not running communication cables here with the current carrying conductors. The tray, not really clear on my picture here, but it continues. So if you actually have multiple charge controllers, you can run the communication cables through here in this smaller knockout, right? Ideally, because you don't want, especially with big systems, as the one that I showed in the previous photo, there will be so much noise on the side of the conductors that are carrying current that it will absolutely interfere with the communication. So it's absolutely mandatory that you're running communication cables through this pre-designed aluminum tray, which is also grounded, by the way. Here we have a view of the wiring compartments and what it will look like in the system. So the first thing I want to point out is this disconnect or PV disconnect. And to meet NEC 690.15, we must break or open both legs, right? Because this array is going to be 1 or 2 strings max. There are some exceptions on the NEC that, depending if you meet all of the exceptions, you don't need to have an overcurrent protection device. However, you must have a PV disconnect. The next thing is the ground fault. So this product comes with a ground fault built in. What will happen is when you receive it, open the box, and you're going to find these fuses already installed here. A fuse on the positive, sorry, this will be the negative side, and you need to remove one or the other. We can't have them both. It's just simply we don't know which one you're going to use. So remove the one that you're not going to use, save it in case you ever have to replace the fuse. 99% of the installations, the fuse is going to go on the negative side. Unless you have a telecom installation, unless you have a very specific requirement from the module manufacturer that says that the array must be positively grounded, then the fuse would be on the positive side. Your typical installation, 99% of the today's arrays are, the fuse is going to be on the negative side. If you have multiple charge controllers, each one will have the fuse installed in the negative conductor. And so what we're doing here per NEC code is that we're bonding the ground and the negative right here on this fuse holder. You don't have to do anything. This is already within the circuit of the MPPT80. So once you put the fuse in there, now you have a bonding. And what we're actually trying to detect is if there is 1 amp or greater in the ground, it will open the fuse and it will give you a ground fault. Some of the reasons why you may have a ground fault: things such as damage on a conductor that has become loose because of wind, has been cut, rodents maybe. I've seen birds' nests under arrays. And so now with a cut conductor, you may have a conductor that is moving with the wind and the rain and is touching the array, the frame of the modules. Well, now I have current on the frame of the module. So that it's a ground fault. So this is why it's per NEC code that you have to have this fuse in place. And like I said, 99% of the time, this fuse will be on the negative side. The next is the BB connection. So I get a lot of questions about this. I don't know if you can see this really well, but it looks like you have 3 points of connection for negative, for 3 strings, and it looks like you have 3 strings or points for a positive. if you wanted to run the wires that way, that's perfectly okay. However, this is one single MPPT. It doesn't have 3 separate MPPTs. So the most common is that once we get to the disconnect, we actually bring one positive and one negative to the PV connections. And the range that the connector will take, you see from a number 6 to number 14, you need to calculate voltage drop. Make sure that the conductor is of the correct size to minimize voltage drop. On the other side, on the battery side, they immediately notice that there is much bigger, that the connector is much bigger and can handle a much bigger conductor, of course, because now we've moved up from 600 volts, which is on the PV side. When the voltage is higher, then the conductor is smaller because you're carrying less current. And now you go to the battery side, and now the voltage will be nominal 48, so you'll have more current. And this will accommodate from a number 2 to a number 14. Okay, let me jump to the Xanbus so I can stay in order, but I wanted to talk about the overcurrent protection device next. So I mentioned that already from the previous slide. This section is not really clear on the photo, but it is a separate tray, and it's intended to run communication cables. Okay, and this bottom piece too is actually another piece of the tray where you can actually run the communication cables and not be running them with the current carrying conductor. So why are we recommending an 100 amp DC breaker? It's because the output of this unit is 80 amps. And we need to multiply that by the safety factor 1.25, which puts us at 100 amps. Caution here that if you have 100 amps, then you got to make sure that the conductor can carry the current, right? Because the job of the breaker is to protect the conductor, not to protect the solar charge controller or the inverter, right? So you got to make sure that per code, the breaker needs to be 100 amps. So then the conductor ampacity needs to match the breaker. All right, so let's talk about the operating voltages of this unit. And for some of you who are familiar with grid-tie inverters, sort of a reoccurring theme here. I'll keep comparing this unit to a grid-tie inverters because it behaves very similar to a grid-tie inverter, except for the fact that it's DC to DC device. But when you look at a grid-tie inverter, you have what we call an MPPT window, operational window, the voltage where the unit would be most efficient, right? So you want to make sure that you string your array so that at all times, right, as the sun is coming up in the morning and setting, you are in the most efficient range of the voltage. So let me point out here, from 0 to 195, this unit is simply going to be off, sleep. If you have less than 195 volts in the array, you will have 0 production. And this is also true on the upper range of the scale. So from 550 to 600, you will have no charging. And this is so that the unit can protect itself, right? Because 600 volts is the maximum. So what you want to do when you're string sizing is you want to make sure that you are in the middle of the range, so that you can actually cover most of the changes. So one of the things that is incredibly important, and it's funny because I get, just this week, I got a question from an installer, and he's like, Sandra, can I put 10 modules for the MPPT80? And the answer is, I don't know, right? Because all of the modules are different. And also, I don't know where the installation is. Because it's critically important for this calculation that I know the temperature ranges. Because I may be calculating off of STC, which is 25 degrees, but what happens when the temperature decreases? Okay, so when you are working with multiple charge controllers, I want to show something that can happen. It's happened often enough where we've added this whole section in the manual. So here we have the correct way to do this dual MPPT80 installation. And what I'm trying to show you here is that each MPPT80 has its own independent array. So I got the positive conductor from array number 1, I got the negative conductor from array number 2, from array number 1, and then the same thing, array number 2, positive conductor, and they're not mixing. Right? What we have seen is some use of combiner box and accidentally crossing. And what I'm showing you here is this mistake is probably one of the most difficult troubleshooting because the units will operate during commissioning. You will actually have all the checkpoints and everything will check fine. But what will happen is because you have the negative of one array connected to the other charge controller and then the same on the other side, is that the MPPT, the maximum power point trackers of the two units are going to be fighting each other. The end result, or how you're going to hear about this, is low production. And every time we get a call from a customer that says, hey, I have low production, I will probably say 99% of the time, this has been the problem. So be mindful of that wire management, because you can actually have a problem if you mix the wires. Okay, so we talked a little bit about the network, the Xanbus network. I just wanted to give you a visual of what it would look like. So here we have the network where we have the MPPT80 daisy chain to the inverter, then the inverter's daisy chain to the accessories. In this case, we have a system control panel, automatic generator star, and at the end of the network, we have the gateway, which is our monitoring and control, and also allows you to connect to the cloud server inside too. In this scenario, all of these devices are talking to each other and sharing information, and I'm able to see all of it in one platform. If you had a DC only installation, this is not required. The controller will operate without needing to be in the network, but there are benefits to have the system in the same network. And as I promised, I want to talk about lithium batteries because they're becoming so much popular. I'd love to hear from you guys. How much are you seeing in your regions lithium batteries? So some of the regions I work in, I am seeing as many as 35% of the systems with lithium batteries. So I got some names here. I have some brands, some logos. But before I jump into telling you the differences between these brands, I want to say that this is not the only batteries that we can work with. You know, sometimes I do these trainings and then I get questions from participants that say, well, how come you guys are not working with this other brand? Well, that's not necessarily that we are not working with them. It's just simply that we are working closer with these brands, but the product can actually work. If the battery manufacturer designed their batteries to be a 48-volt nominal battery and it has a BMS, it's most likely going to be okay to work with the Schneider Electric Connects products. You can always reach out to us and we can always give you our recommendation. But the battery manufacturers that I have on the screen here are batteries that we have been working with for years. These are batteries that have done a lot of work so that they can be optimized in the system. Between the two groups, you see this group here, which I'm calling the open loop integration, and then I have this other group that I'm calling the closed loop integration. I will explain what that means in the next slide. But I can tell you that between this group of batteries, we have thousands of systems from all the years. I want to say some of these brands I've worked with for 6-7 years. So this is definitely a shift in the industry. We were primarily a lead acid battery, but slowly these batteries are becoming more and more competitive. We are still working with lead acid batteries. And if I honestly, the majority of our system are still lead acid battery, but depending on the region, we are starting to see the shift. So let me explain what I mean by open loop and closed loop integration. So in an open loop integration, the battery is lead acid replacement. It means that it just simply behaves like a lead acid battery, and it doesn't have to have any type of communication with the Xanbus network. It accepts the voltage, the battery manufacturer will give us the set points, we program the set points, and that battery will behave just like a lead acid battery. With a closed loop integration, you see now I'm showing a communication cable that has gone the AC chain from my charge controller to the inverter, and then to the accessories, and then to the battery. So now this battery is in my network. And that network can be directly Xanbus network, which is what Discover does, or what many others do is Modbus with the gateway. What does this battery communicate? Depends on the brand of the battery, but the idea is you plug it into the system and the battery tells the inverter and the charge controller the optimum settings. And then you have a variation of that depending on the battery manufacturer. Some of them actually actively tell the inverter and charge controller what to do. Some of them just simply tell them what voltages they like. So that's the differences between open loop and closed loop integration. We're actually doing a lot more work with more batteries, and hopefully the next time you attend one of my trainings, you might see that slide with way more logos. So the last thing quickly I want to show you is the programming. I've already mentioned that the unit itself, it doesn't have a display, so you need to access the programming either using the system control panel or the gateway. What I am showing you here is the menu structure of the system control panel. On the next slide, I will show you the menu structure for the gateway. The settings are the same. For a battery, my recommendation is always set the battery charging settings, mandatory, during commissioning. You only do this one time, then it gets recorded in the non-volatile memory. Even if you turn off the unit, it will still remember the settings. The next recommendation is always select the battery type custom. Although when you look at the menu, you're going to find some presets, flooded, AGM, and gel, presets from the factory. And if you select them, you can't make any changes. This is why I recommend you always use custom. Once you select custom, then all of this menu becomes available to you, and now you can actually program each one of these settings exactly as the battery manufacturer is recommending. Next one is using the gateway. And although the screen looks a little bit different than what the menu structure of the system control panel, the settings are exactly the same settings, right? So we're going to actually program exactly the same settings. And again, I recommend that you always select custom. Okay? And the last thing I want to touch on is for you guys in the North America region with requirements for rapid shutdown, NEC 2017, rapid shutdown. So we meet 690.12, which is rapid shutdown, as well as 690.11, which is arc fault, with our newest MPPT Disconnect RS. So you actually have three things in one with the Disconnect RS. So you have the rapid shutdown, you have the arc fault, and you actually have a PV disconnect. So the little animation I have here on the screen, you see normal operation of the array, And now I'm going to simulate a rapid shutdown. So you see the initiator button has been flipped. And now because the rapid shutdown disconnect RS is in the network with the devices, everything shuts down. The array shuts down to the required 80 volts in 30 seconds. They beyond up to the DC disconnect to 30 volts for 30 seconds. The MPPTs and the MPPT and the inverters goes into an off mode. So everything shuts down by the simple switch of the initiator. This is a little bit more with the architecture where you'll see the inverter, charge controller side by side. Traditionally, we would have a PV disconnect nearby because per code can't be on the roof, it has to be nearby. And so what we're doing here is replacing that disconnect for the MPPT Disconnect RS. So 3 things in one: rapid shutdown, arc fault, and PV disconnect. This product, by the way, is also compatible with the MPPT60. Today, I was only talking about the MPPT80, but it is also compatible with the MPPT60. You can have as many as 2 of the MPPT80 with 1 of the disconnect RS. So you have 1 initiator, 1 disconnect RS per unit. On the roof, under each module, then you have the Tigo F series, which are communicating with the Schneider Disconnect RS via power line. So you don't need to run a communication cable. There's no need to run a communication cable. You just simply mount these under each one of the modules, and then the disconnect will be triggered by the communication over the power line. Because the RS disconnect is in the Xanbus network, it also shows up on the gateway interface as well as inside too. So you actually can see which state it is, if it's actually trigger a rapid shutdown or if it's a normal operation, because it is connected in the same network. Right, we get to the end of the presentation. Thank you so much.